Hey guys, here is our second video lesson of the unit. This one goes over all the other types of trig functions in terms of graphs. So let's go ahead and get started. Graphs of other trig functions. Now, our warm-up here was to figure out the properties, the transformations of these two functions, and then graph two period intervals for each. So I'm going to go ahead and do that. So 3 cosine 2x means the amplitude has been changed to 3. The period is 2 pi over 2, which is pi. Everything else stayed the same. So on my graph, 2 period intervals, so I'm going to have pi there, 2 pi there, half, 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 half. Going up to 3, down to -3. Oops. And let's see, let's go with red for our line. Cosine is going to start at the top and then end its wave at the top. So 2 period intervals, cross, bottom, cross, cross, bottom, cross. So it looks something like that. All right. Let's see. Sine of x plus pi minus 1. So midline of -1, phase shift of -pi. So sine graph normally looks like this. So a plus pi is going to start us right there in the middle, going down. Let's see, period is still 2 pi, was not changed, so 2 pi, 4 pi. Amplitude was not changed, so it's just 1 and 1. The phase shift, or sorry, the midline was changed to -1, so I need to go down to -2. Oops, chose the wrong color blue there. So this is my midline, here's my top, here's my bottom, and instead of starting in the middle going up, it's going to start in the middle, go down. Oops, almost forgot to make my markings. So, oops, it's messing up all over the place here. Like that. All right. So in this one, we're going to talk about all the other types of trig functions. So we have graphs of tangent and cotangent. And these work relatively the same as the sine cosine in terms of the transformations. However, you can kind of tell there is no longer an amplitude since it goes forever up and down. But there still is a period. There still is a midline. Okay, the midline is kind of the middle of the wiggle, I call it. How the tangent function kind of wiggles through the midline. And then that midline can move up and down. The period can move, can shrink and grow. The phase shifts, that all kind of works the same way with a couple of changes. So the properties. So like I said, period and midline are still important, but you can see there is really no amplitude anymore. Also, the period of a standard tangent cotangent wave is pi. So the period for a tangent cotangent would be pi over b rather than pi or 2 pi over b. So it's 2 pi over b for all the other functions. It's pi over b for tangent. And you won't have to worry about graphing these by hand. You'll just have to be able to match them up. So a couple of key differences between tangent and cotangent are the fact that tangent goes up and cotangent goes down. So if you look at this, the green lines are the cotangent going down, negative slope, tangent going up. Main difference, and then you can kind of figure out your period and stuff like that from looking at the graph or the equation. So, from there to there where it's crossing its midline, a period of pi. The standard period. So And that's all we're really doing for tangent cotangent. You just got to be able to recognize it. Looks way, way different than sine, cosine, secant, cosecant, so it should not be hard to not mix that up. Now, the secant, cosecant are a bit different. So it makes it look like there are an infinite number of alternating parabolas. So up, down, up, down, up, down. Looks kind of weird until you match it with its corresponding sine or cosine. So comparing cosecant and sine makes more sense. Okay, we have our sine wave, and every time that sine wave has a min or a max, it creates a parabola. Every time that sine wave crosses its midline, it creates an asymptote. So you can see how the asymptotes are separating the parabolas. So if you can graph a sine or cosine, then you can graph a secant, cosecant. Okay. So here's an example where we have 2 cosecant 2x plus 1 and 2 sine 2x plus 1, and they both match up perfectly. Once again, everywhere the sine wave has a min or max, the cosecant will have a parabola. Everywhere the sine wave crosses its midline, the cosecant will have an asymptote. So let me draw those in. Be careful to make sure that you are only looking at where it crosses its midline, not necessarily where it crosses the x-axis. Okay, that's a very common mistake. If you start doing that, so like if you try and put an asymptote right there, it's going to cross through your parabola. So that's not right. So let's go ahead and graph one out across 2 period intervals. So 2 secant 0.5x. I'm going to graph the corresponding cosine first. Okay, let me change up my color. Let's go with blue. Yeah, purple's good. So I want to identify everything we did in the warm-up. So our amplitude is going to be 2. Our period is going to be 2 pi over 0.5, which is 4 pi. So on my graph, 4 pi in the middle, 8 pi, middle, 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 and goes up and down 2 from 0 because the midline has not changed. So I'm going to draw some dotted lines. And this will give me my cosine wave. So let me do my cosine in red. So it has not been phase shifted, so it's going to start at the top, end at the top, end at the top. So cross, bottom, cross, cross, bottom, cross. And there we go. So that is my cosine, so obviously I'm not done. I am going to draw myself asymptotes everywhere it crosses the midline. And let's make our cosecant green. So the only thing that really matters in the end are those parabolas, but everything else is the work you show to get to those parabolas. Okay. We need to talk about domain, range, and period of trig functions. So depending on the trig function, changes things up slightly, but it's not terribly complex. So if you're dealing with a sine or a cosine, it's relatively the same thing. So period, in this case, is going to be 2 pi over 3. Let's see, domain of every single sine and cosine is just all real numbers, and range is going to be the range from the midline minus the amplitude and then the midline plus the amplitude. So in this case, -1 to 3. And you can see that on the graph. The lowest it goes is -1, the highest it goes is 3. Okay, it goes forever left and right, so domain is all real numbers, period, 2 pi over 3. And then the range takes a little bit of calculations. Now, just like graphing, if you're told to graph a cosecant, then you would do the sine first. Well, if you're doing domain and range of a secant, it's helpful to know the sine first. So let's do the same thing. Domain and range of 2 cosecant 3x plus 1. And let's see how it matches up. So the period is the same thing as the other period, 2 pi over 3. The range is almost the same thing, but it's the opposite. Instead of between -1 and 3, it's going to be -infinity, -1, and 3 infinity. So we get those two numbers over there. And then domain, since I saved it for last, is the trickiest one. In sine and cosine, domain is all real numbers. In secant and cosecant, it is all real numbers except the asymptotes. So in this case, x cannot equal. And then let's look at our asymptotes. Now, there's an infinite number, so it's kind of impossible to list them all, but we want to list a pattern. So it goes left and right, and it's a mirror image. So we're going to do plus minus, starts at 0, and then if you notice, it hits the midline every half a period. So half a period, so the period is 2 pi over 3, half a period would just be pi over 3. So pi over 3, 2 pi over 3, 3 pi over 3, etc. Okay, so that's the tricky part. Domain, you have to list out the asymptotes that x cannot equal. Similar thing for tangent, cotangent. Okay. All right, so let's go ahead and do it a couple more times. We're going to do the sine and cosecant of the same thing so you can see it connected. So period of each should be the same thing. 2 pi over 2, which is pi. So period over here is the same thing. Over here, domain is all real numbers. Over here, domain is all real numbers except x cannot equal plus or minus 0, pi over 2, 2 pi over 2, etc. So remember, I got that pi over 2 because the period is pi, and so it's half periods. The asymptote shows up every half period. And then over here, the range is going to be from midline minus amplitude to midline plus amplitude. So -1 to 5, which means the range over here is -infinity to -1, and brackets 5 to infinity. Okay. Now, let's move on to our inverse trig functions. So we have all the other graphs going on. Now we got to talk about the inverse. Now the inverses do have graphs, but they're not incredibly helpful. So we're not so much going to worry about them. We're just going to worry about using the inverse trig functions. The graphs themselves help you understand why there are restrictions on domain and range, which if you think about it, an inverse function takes the domain and range of a function and swaps it. So if you look at sine, domain is all real numbers, range as a restriction, and so the inverse function would be inverse sine. The range would be all real numbers, domain would have to be restricted. So because of that, we wind up restricting the range also. Now, it's not something you need to memorize. However, one thing I want to make a note of before we go on is that there are two ways to write the same function. Sine -1 means inverse sine. Arc sine means inverse sine. Same thing for cosine, inverse, arc cosine. There's an arc tangent, arc cotangent, all the above. Okay. So just to take a look at the graph, like I was saying, there is a restriction. So this is the inverse sine graph, and we restrict it to one half cycle, because technically this sine graph would go that way and that way, but then it's no longer a function. Okay, it wouldn't pass the vertical line test, so we restrict it, and then we only get ourselves one answer. Now, each of the trig functions is restricted in a different way. And so what we're going to do is take a look at this. So we have arcsine, arccosine, arctangent, arccosecant, arcsecant, arccotangent. Domain restrictions are important to know, but they're not very complex. Range restrictions are what we really want to make sure we know. And if you take a look at it, there are some repetitions. So let me get rid of those real quick and show you the repetitions. So we have negative pi over 2 to pi over 2, negative pi over 2 to pi over 2, negative pi over 2 to pi over 2. With this, you don't need to worry about that so much. And then we have 0 to pi, 0 to pi, 0 to pi. So we have our restrictions, and what this does for us is it separates out the unit circle, and it tells us what quadrant we're in. So if we think about our unit circle, this is 0, this is negative pi over 2, this is pi over 2, this is pi. So the negative pi over 2 to pi over 2 functions are going to be over here in the first and fourth quadrants. So that is the inverse sine, inverse cosecant, and inverse tangent. Lives in first and fourth quadrant. The other ones live in first and second quadrant, 0 to pi. So cosine inverse, cotangent inverse, secant inverse. So each one of those also has an appropriate location where it's plus and minus, so you can always know which quadrant you are in, so that when you're looking on your unit circle, you know where to look. So we're going to look at this in a couple different layers of difficulty. We're going to look at just strictly how to use the inverse trig functions as they are. And also to look at composition of functions, so putting inverse inside regulars, and vice versa. So these three problems right here are straight up unit circle problems. So arcsine negative 1 over 2, inverse sine square root of 3 over 2. Remember that arc sine is the same thing as inverse sine, and then arc cosine 2. It's missing a C, arc cosine 2. So we've done these since early on in the first unit this semester. So I'm going to bring up my unit circle right there. And I'm looking for negative 1 over 2. And so the y values being negative 1 over 2, I have one right here and one right here. So the two possible answers are 7 pi over 6 and 11 pi over 6, kind of. But here's the thing. We just talked about the fact that inverse sine is restricted to quadrants 1 and 4. And that means this quadrant will not be used for any of these problems because it's not, none of the functions are restricted to that quadrant. So that being said, this looks like it'd be our answer. However, take a look at that angle measure, 11 pi over 6. To get to 11 pi over 6, we have to go outside our restricted range, and so we can't do that. Instead of going that direction, we are going to go, oops, need my, not getting my highlighter back. We want to go, I'm not sure why it's not getting my highlighter back, but it is what it is. Now, what we want to go is the opposite direction, so from 0 down there, and so instead of 11 pi over 6, it's going to be the coterminal angle of negative pi over 6. because instead of going all the way around the circle into the restricted area, it's going to be the coterminal instead. Let's see, inverse sine of square root of 3 over 2. Let me get rid of my stuff. See if it'll let me do the highlighter again. Okay, so square root of 3 over 2. In the y value, we have one right there. We have one right there. However, we cannot be over here for the inverse sine, so that's our answer. And since we can get there without leaving our restricted area, then we can just use that pi over 3 as our answer. Okay. And lastly, arc cosine of 2. So we want to look at our unit circle and find where the x value is 2. Hopefully you realize there's going to be an issue there. The x value can never be more than 1 or less than 1. Remember, we have domain issues. More than 1, less than 1. 2 would be way out here on the edge somewhere. So we can't do that. So instead, we realize that arc cosine of 2, so arc cosine is outside the domain restriction, and so we say no answer. Okay, and if you try to plug that into your calculator, you would get a what's it called? A domain error. It would error out on you. Speaking of which, these are all exact value problems. Exact value means unit circle, no decimals. Okay. Up next, approximate value means calculator. Means you would not be able to find your answer otherwise. Now, depending on which arc function or inverse function it is, it determines whether or not you can just straight up type it in as is. Now, your calculators have buttons for sine, cosine, tangent, and then most of them, if you're using graphing calculator, you see up above those buttons inverse sine, inverse cosine, inverse tangent. So if you're using a graphing calculator, you just hit second and then that button. So if I'm doing arc tan 1.5, I'm going to hit second tangent 1.5, enter, and then I'm going to put myself in radian mode just because I get 0.983 rounded. If you're not in radian mode, you would wind up with 56.31 rounded. So this is radians, this is degrees. Remember, what you're finding is an angle of rotation. And so it really depends on whether or not, the problem tells you radians versus degrees. Now, cosecant -1 of 10. This one you cannot type in as is because you do not have an inverse cosecant button. However, cosecant matches with sine, and you do have an inverse sine button. So instead of typing it in like that, you are going to type it in as inverse sine of 1 over 10. And so that gives us, let's see, in radian mode, 0.1. In degree mode, that would give us, let's see, divided by 10, 5.74. So just make sure that you know how to use your calculator, that you know where the buttons are and you know how to type stuff in, and then just double check the mode you're in compared to the problem itself. Now, let's talk about composition of functions. There are two different varieties. This one I call the easy-ish function, and that is when you have the inverse on the outside and a regular on the inside. So the exact value of the function below, we are going to do a unit circle solution. Now, we have to look at the unit circle twice to do this. Arc sine and sine don't necessarily cancel each other out. So you cannot just say, hey, it's the inside. Sometimes you can, sometimes you can't. Let me show you why you can't. So first, we are going to figure out what sine of pi is. And so I'm going to go to my unit circle, and find pi, and sine is 0. So that inside becomes 0. Now I have arc sine of 0. And so what I'm going to do is I'm going to look here and figure out where else I have a y value of 0. Oops. Now, of those 2 points, only one of them is inside the restriction. Because remember, inverse sine is restricted to the first and fourth quadrants. Therefore, we cannot use this point over there. So my answer is 0. It's either 0 degrees or 0 radians, depending on the problem. Okay. So arc on the outside, regular on the inside is straight up a unit circle times 2 problem. Okay, and we'll do a couple more of those here in a minute. Oops. Arc on the inside, regular on the outside, so regular arc, is a bit more challenging. And this is a triangle problem. So let me show you what that means. So the exact value of the function below, arc cosine of 2/3. I'm going to draw a triangle, and cosine is adjacent over hypotenuse, so if this is my angle, 2/3. And now I want the tangent of that triangle. So this produced the triangle, and then I want the tangent of the triangle, so I need that value right there that I'm going to call y, and then it's a Pythagorean theorem problem. So 2 squared plus y squared equals 3 squared. 4 plus y squared equals 9. Y squared equals 5. So y equals square root of 5. And so tangent of that is square root of 5 over 2. And then the last thing we got to figure out is what quadrant were we in, so we know if our answer is positive or negative. So arc cosine is restricted to the quadrants 1 and 2. Of those 2 quadrants, well, this fraction is positive, so of those 2 quadrants, cosine is positive only in the first quadrant, becomes negative in the second quadrant. So a positive arc cosine means first quadrant. So first quadrant. And then so our answer is going to stay positive. If we were in the second quadrant, if that were negative 2/3, it would be negative square root of 5 over 2. And lastly, let's just go ahead and go through a few. Make sure you know what you're doing. So I'm going to start with the ones on the left, which are triangle problems, arcs on the inside. So the cosine of arc sine 1/5. So triangle, sine of 1/5, so opposite adjacent. That's our angle. Cosine, I need that value. So x squared equals, let's see, 25 minus 1 is 24. X equals square root of 24, which can be reduced to 2 square root of 6. So adjacent over hypotenuse, 2 square root of 6 over 5. Okay, so triangle problem, complete the triangle, put the fraction together, and then check and see if it's positive or negative. So the arc sine is positive, therefore the cosine is positive, because we're in first quadrant. Down here, tangent of arc secant, 3 over 1. So secant is the opposite of cosine. So instead of adjacent over hypotenuse, it's hypotenuse over adjacent. And I need the y value. It's tangent again, which, didn't we just do this one? Nope, looked like it. Never mind. So let's see. 1 squared plus y squared equals 3 squared. So that's 9 minus 1 is 8. So y is square root of 8, which can be reduced to 2 square root of 2. And that gives us an answer, so 2 square root of 2 over 1, which is just 2 square root of 2. Okay, other 2 problems are unit circle problems. So do the insides first, turn that into a number. So let's look at our unit circle. Let me get rid of my stuff. And let's see, sine of pi over 3. So we'll do the top right one first. So pi over 3 is right here. The sine is square root of 3 over 2. So square root of 3 over 2. So I want to find the cosine of that. So everywhere the x value is square root of 3 over 2. So that's right here and right here. However, the arc cosine is restricted to up here. We cannot be down there. And so that's where we get that as our answer, pi over 6. Down here, cosine of 2 pi over 3. So 2 pi over 3 is right here. Cosine of that is negative 1/2. We want the arc sine of negative 1/2, so we find all the points that have a y value of negative 1/2. That's going to be right there and right there. Well, we kind of already did this one. So sine is restricted, cannot go through there or in there, so we have to get there going this way. So that's the negative pi over 6. So, thing to remember here, if the arc's on the inside, it's a triangle problem. If the arc's on the outside, it's a unit circle times 2 problem. So, that is it for this lesson. I'll see you guys in class.